Hey friends, today we're going to do binomial probability, and it's pretty cool because we're finally getting to a little bit like a very early beginner thing of what I like to do in my program and what I'm very interested in terms of modeling experiments and how things can come out. I use the binomial formula all the time, and this is also the last lecture of the school year. Unless you guys want me to go over some more statistics stuff. And my feeling on this is just this. I'm going to default to no more. Unless one person at least asks me to. If anyone at all asks me to, I'll do it. But if you guys are done, and that's perfectly fine, and you just want to relax and start your summer vacation, there's zero judgment on my end, and there will be no more, okay? But if one person says, I really would like to learn a little more statistics, then I will gladly do another week of lectures for you guys, along with another extra credit something at the end. Okay, so binomial experiments. Let's talk about these. Binomial makes a lot of sense as a word. Okay, nomial is like number, and bi means two. Right? So it means there are only two numbers, only two possible outcomes. So I'm gonna one example of this is if you flip coins, right? If you flip a coin, there are only two possibilities for that coin. It can either be heads or it can be tails. And you can represent the probability of the outcome of a coin with the binomial formula that we'll talk about shortly here. In fact, I'll scroll this down right now so I can fit more stuff on the page all at once that I want to talk about. Yeah, this is perfect. Okay. And so, let's say that I have an even coin, okay? And I want to say, what's the probability of getting heads versus tails? Well, the probability of both of these is 0.5, right? But let's say what if I ask a different question? What if I say, I'm going to flip a coin twice? What are all my possible outcomes, and how often will they happen? Okay, I can get heads or tails on flip one. Then after that, I can get another heads or tails. So what are my possible outcomes? Heads is 1. And I can get heads, tails. I can get tails, heads. And tails, tails. And these are all equally likely, right? They each have a 1/4 chance of happening. Except there's a little something. What if I generalize a bit? And instead of saying, what are my possible outcomes and what are their possibilities? What if I say, what's my probability of getting, how many heads can I get? And what are my probabilities for getting those heads? Okay? Then this has 2 heads, and something interesting happens. Heads, tails, and tails, heads each have 1 head. And tails, tails has 0. Well, that means so if I say, what's the probability of getting a heads, it's 1/4, which is 0.25. And the chances of getting no heads is tails, tails, and it happens 1/4 of the time too, 0.25. But if I say, what's the probability of getting 1 head? There are 2 situations where I get 1 head. The 0.25s combine, and there's a 50% chance of getting 1 head. Okay? I'm going to model this a little bit. And when you do this, you end up with a probability chart called a histogram that looks kind of like this. Okay? So what I'm going to do here is I have this command in my software called rbinom. And rbinom generates n sets of results of a given size and a certain probability. So I'm going to do I'm going to save this as saving it as the variable a. our binom, and I'm going to do 1,000 coin flips in groups of 20. So this is doing 20,000 coin flips. It's going to do 20 coin flips, and then it's going to bucket that, and another 20 coin flips and bucket that, and it'll do that 1,000 times. And we want our coin flips to be a 50% chance of getting heads. It just did it. That was 20,000 coin flips. And if I hit A, these are all my results. This is 1,000 grouped results. So you can see in here, for example, I'm trying to look for a 20 in here or something. Didn't I get any 20s? Did I get no 20s? Let's try it again. Well, regardless, you can see these different numbers, and these are the different total number of heads. Okay, so I did 20 rolls at a 50% chance of getting a head, and my first set of 20, 9 of them came up heads. Then 9 came up heads, 12 of them came up heads, 10 came up heads, and it did that 1,000 times. Okay, and this is, if you look at this, this is incomprehensible, right? You can't tell what's going on here. So I can make something called the histogram, which tells me how often everything happened. So this histogram, I can modify it further. And this hist command is actually what I use when I do your grade distributions that I show you guys throughout the year. This histogram right here shows me how often each thing happened. Okay, and the 10 is here, but it's for this number right here. So how often did 4 happen? You know, the frequencies aren't written out. This is like the default histogram. I haven't coded it to be very specific and clear. But you can see the chance of getting only 4 heads out of 20 at a 50% chance is very low. We only got 4, you know, like, I don't know how many times that is. Not many, okay? Maybe like 10 times. And then what are the chances of getting 16 out of 20? Extremely small. But 10 is getting half of them, right? And we would expect in 20 coin flips, when there's a 50% chance of getting heads, which with each coin flip, that a lot of them would be around 50% of 20, which is 10. So notice around 10, there are lots. Okay, and if I do it again, oops, wrong thing. If I do it again, the histogram is different, but notice the same shape is there. Okay, this shape is what we call the binomial distribution. Okay, I'll do one more. I could do this all day. I find it so fascinating. So here's my binomial distribution. And notice if I do fewer sets of flips, notice that it's less smooth. That was still pretty smooth, but oh, it kind of looks like it's flipping me off. But notice how this is a huge peak in the middle, and these are lower. It's not quite as smooth. But what if I add some zeros? Let's do 100,000 sets of 20. Notice how fast that was? My computer's great. 100,000 sets of 20. If I histogram that, look how smooth this is. And look how even these levels are. Look how even these levels are. Look how even these levels are. Like, everything looks very even. So the more sets we do, the less randomness there is in our set. Things tend to even out. This is called the central limit theorem, just an FYI. If I do it again, I think this will look very similar. See how much it changes in my new set of rolls. Not a big change, huh? It looks pretty much the same. Looks pretty much the same. So I do lots of rolls, or lots of coin flips, excuse me. Yeah, if we do lots of coin flips, it looks very similar. If I add another 0, let's make it 1 million. It's already done. If I do 1,000,000 coin flips, see, it still looks the same. Right? It looks identical after 1 million. So 100,000, 1,000,000 coin flips end up looking at the same when we do a distribution of where their values end up. okay? But if I'm only doing, let's do 10. Okay, what's 10 look like? Right, that looks terrible. That doesn't even look like a binomial distribution, because it just so happened that I got numbers that were improbable. That's going to happen. So you look at that. That's another roll of 10. That 10 looks nothing like my previous 10, because I got different sets of numbers. The other set of 10, if you didn't notice, didn't even go below 6. Now I got 2, you know? So that's the idea between the binomial theorem, okay? And the way that's done in these notes, although it isn't the way that I like to do things, is there's a probability of success, which is P, and a probability of failure, which is Q. I usually just use 1 minus P, because it's probability, and it adds to 1, right? So I have 2 variables. So instead of Q, I might write 1 minus P instead of Q. This is just common sense. You know, what's the chance of getting January versus not January? The chance of success is P. So what's my chance of getting January if I randomly select a month? 1/12. What's the chance of getting not January? 11/12, right? It's just basic probability we already went over. The formula for calculating the chance of getting a certain number of successes in a certain number of trials is N choose R times our probability of success times our expected number of successes times our failure rate times our number of, or raised to the power of, did I say times for the R? I meant raised to the power of R. I don't know if I said times, but P raised to the power of R times Q raised to N minus R. Now, again, I think it's just better instead of Q to do 1 minus P. So I'll rewrite that as 1 minus P. Okay, and this is actually very intuitive. I know this looks like a disaster to you, but it's actually very intuitive, okay? Go back to our idea of independent events. If my events are independent and I want to know what the total probability of them happening is, I multiply everything together, right? So this part of the formula, this is just me multiplying all the events together. And P raised to the rth power, that's my chance of probability, raise the number of times that, P is my probability of success, raise the number of successes I expect. And then 1 minus P, that's my probability of failure. If I take my total number, N, of trials, and I subtract from it the number of successes, that's my failures. So N minus R is my number of failures. R is successes, N minus R is number of failures. I don't actually use N and R when I do my math, but I'm just using it because it was used on the cheat sheet for this and what the person wanted written there. Anyway, so if I take, so this is all of my successes, all right, plus here, this is my successes, and these are all my failures. Well, if I multiply my successes and failures together, don't I get the total probability of an entire event occurring? Right? This is like in the bag of marbles, red and yellow. What if I said red and not red? This is like red and not red. Successes and failures. Why is there a combination here? Because when we did our previous example, where I had heads and tails, tails and heads, I had to combine these because they were both situations that had one head. So this combination calculates how many ways we can get our successes. Because we're not just calculating, like if I say, let's do this for example. Say that I want 3 heads and 2 tails, where heads is success and tails is failure. If I do the math for this, what's my probability of heads? It's 0.5. And I want 3 successes. Times, what's our probability getting tails? 1 minus 0.5, which is still 0.5. And what's the probability of getting the tails? Or how many tails do I want? I said I wanted 2. Okay. If I do this math, this is 0.5 raised to the 5th power, which is a very small number that I'm not going to bother to calculate. Does it seem reasonable that the probability of getting 3 heads and 2 tails is extremely small? It should be pretty small because there's so many combinations. But can't I get, for example, aren't there many ways to get 3 heads and 2 tails? Can I do heads, 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 tails, tails? But also I could do heads, tails, heads, tails, heads. And what we want to know is how many combinations of heads and tails are there? Because each of these counts. And I have to multiply the probability of this happening at all by the number of ways it can happen. And this is the number of ways that it can happen. So my total probability, my n choose r, I have to do, how many am I doing? 5 factorial divided by n minus r factorial. That's 5 minus 3, so 2 factorial, divided by r factorial, which is 3 factorial. So you have 5 factorial divided by 2 factorial, 3 factorial. What is that? Let's go to factorial 5 divided by factorial 2 divided by, oops, there shouldn't be a parentheses here. I'll get an error. Divided by factorial 3 is 10. So there are 10 combinations of heads, heads, of 3 heads, 2 tails. 10 different ways we can arrange it. So when this probability, 0.5 raised to the 5th power, when I do that, I get, oops, I didn't mean to do that. I get 0.03125. That's the probability of getting one of the combinations of 3 heads, 2 tails. But I can have 10 different organizations, those 3 heads, 2 tails. So it's 10 times. It's 10 times or 0.3125. So about 30% of the time, we'll get 3 heads, 2 tails. And that makes sense. It makes sense because when we did our previous histograms, things that were closer to the center. In fact, here, actually, let's do this. Let's do 5. Okay, so I'm doing 1 million sets of 5 flips at a 50% chance of getting heads. If I do that, here's what it looks like. Notice this. So this right here, let me erase all this other stuff. Let's plot out what's going on this histogram. This is the number of successes, A. Okay? So this is 0 successes. So this right here, this is tails, 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 tails. 5 successes over here, this is heads, 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 heads. Why are these the lowest? They're the lowest because there's only one way they can happen, right? I can only get tails, 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 one way, getting 5 tails in a row. I can get heads, 5 heads one way, 5 heads in a row. This right here, this is 1 head. Right? This is 1 head. How many ways can I do that? Well, if I have heads, tails, 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 I can do it 1, 2, 3, 4, 5 ways, right? The head can be in 5 different places. So I'd expect this right here, to be about 5 times this value. And it looks about that, right? If you take this and you did it 5 times, Yeah, it's pretty awesome, pretty perfect, right? Right? This is about 5 times this value. Why? Because there are 5 combinations that allow for this. And similarly, this is 4 heads. How many combinations of 4 heads do I have? Well, this is tails, heads, heads, heads. This is the same thing as this, right? There were 5 combinations of heads of 1 heads. There are also going to be 4 combinations of 4 heads. Why? Because the only thing that matters is where the tail is. There are 5 combinations. 1, 2, 3, 4, 5. So we expect this to be the same height as this. What about these two? Well, this is 2 heads, and this is 3 heads. We expect these to be the highest. Why? Because we gave a 50% chance of success. So we expect the heads and the tails to be about even. They can't be perfectly even because there are 5 rolls, right? But they should be close to even. So the closer our values are to even, the more likely they are to happen. And we already did the combinatorial for 3 heads, 2 tails. How many ways can it happen? 10 ways. Well, wasn't this 5 ways? If this is 10 ways, don't we expect this combination to be about double this combination? And indeed, I would say this bar looks to be about double this bar. By the way, I'm really enjoying myself, and I hope you guys are too. This is really interesting stuff. And I understand, at this moment, you're probably thinking, this is amazing, Mr. Dufresne, and I've never learned something more incredible in my entire life. Thank you for doing this. And I'm going to say, you're welcome, child. You are welcome. But you're thinking, who cares about coin flips? And that's a fair question. Who cares about coin flips? Well, outside of a few situations like gambling, it's really not that important. But it doesn't have to be coins, okay? I've been doing coin flips because it's familiar to you. But binomial theorems can also be done to represent anything that can be described as a success or a failure. For example, I'm working on a modeling project to predict end of course test scores for my students, just for fun exercise. And your test results on the end of course exam can be expressed in one of 2 ways, right? You pass it or you fail it. I could express your score as a percentage, or I could express it as a numerical score. I could express you as a level, right? Whether you're level 1, level 2, level 3, level 4, level 5. But what really matters in the end is whether you pass or fail. So I can represent the probability of you passing your end of course exam as a binomial probability. Okay? And how do I get the probability of it happening? Well, that's the more complicated stuff. We're not going to go over that. That's a lot of stuff. But the point is, I can represent your ability to pass a test using this probability theorem. I can also do it for, what are your chances of having cancer? What are your chances of getting coronavirus if you go to a crowded area? And so on and so forth. Anything you can describe as happens or doesn't happen is binomial. And that means you can fit a lot of things into that. Okay, so coin flips, not that important, not super useful in a lot of situations. But the coin flip is a specific situation of the general binomial distribution. And the binomial distribution is extremely useful. Okay, so I'm just going to, I'll do one example here. And so this says, Mark tosses a coin 25 times. Oh, let's not do, well, okay, maybe I'll do 1 and 2. We'll do coin and I'll do a spinner. Coin 25 times, what is the probability that it lands on the head exactly 7 times? So it's a 50% chance, so I have 0.5 to the 7th power. That's my chance of success, and it succeeding 7 times. And my chance of failure is also 0.5. And how many times does that happen? 25 minus 7 times. My total number of times minus my successes gives me my failures. And then the combinatorial, I'm doing 25 different combinations. Okay? And I want to talk about how many different ways I can succeed. My successes are the 7 factorial. And I also want to talk about how many ways I can fail. 25 minus 7 factorial. So if I do this, I'll get my answer. And what's really nice is that in my program R, let's see, 7 successes. I can just do, there's a command for combinations. Instead of doing, I can do factorial 25 divided by factorial 7 divided by factorial 25 minus 7, and I get 480,700 combinations. You don't want to do sample space for that, but I can also just do choose 25 7, and this is 25 choose 7, 25 combinations, 7 success combinations. Notice that this is the same thing as 25 choose 25 minus 7. Pretty nifty, huh? Because it doesn't matter. So 480,700. And then, oops. Ooh, no. Here we go. This is my probability, right? 0.5 raised to the 7th power times 0.5 raised to 25 minus 7. So I'm going to do choose 25 7, which is the same thing as this factorial up here. I'm just using a command to make it shorter. Times 0.5 raised to the 7th times 0.5 raised to the 25 minus 7. And that is the probability of it happening. 0.014. Plus all the other stuff. Okay. So what is the probability? And then let's add the mass library, and I can tell R to express this as a fraction. Yeah, that's my fraction right there. Okay? That's the probability of it happening. You could just write it as 0.014, okay? Your test instructions should make it clear. So let's do one with the spinner. The spinner is spun 10 times. What is the probability that lands on red exactly 6 times? So, first of all, how many do I have? 1, 2, 3, 4, 5, 6 possibilities. So my possibility of success is something out of 6. And how many of them are success? I have 1, 2 reds. So 2 out of the 6 are successes. And I want to know, what's my chance of doing that 6 times? So I want my 2/6 chance of success 6 times, times, what's my chance of failure? 1, 2, 3, 4 out of 6. And how many failures do I expect? If I'm doing 10 spins and 6 successes, then 4 of those will be failures. And my combination is going to be 10 factorial divided by both my successes and failures to keep track of how many there are total. Okay? And then you just type that math into a calculator. Okay? I won't waste time doing that. The other question we can ask about binomial, and there are lots of questions to ask, but another common question is, what is the probability of not getting 8, but getting 8 or more? So what does that mean? I actually do 3 different calculations. Okay? So what's the chance of getting 8 successes? And I'll do this green. 8 successes, 9 successes, and 10 successes. I have to calculate all those and add them together. So what's the probably getting 10 successes? Well, I have 10 different combinations, or 10 factorial, 10 different coins that I'm gauging true and false for, divided by my successes is 10 factorial, failures is 10 minus 10, or 0 factorial. Okay, remember this is 1. And then I'm saying there are going to be 10 successes. So it's 0.5 raised to 10, and 0 failures. 0.5 raised to 0. Remember, anything to the 0th power is 1. For the 9 then, right, I have to do 10 factorial divided by 10 minus 9, or 1 factorial, and the 9 factorial. And then this is going to be 0.5 raised to the 9th and 0.5 raised to the 1st, because there's only 1 failure. And what if there's 8 successes? Then it's 0.5 raised to the 8th power and 0.5 raised to the 2nd power, and then I do 10 factorial divided by 8 factorial and 10 minus 8 factorial, or 2 factorial. I gotta calculate all of these. Okay. Luckily, these are both 0.5s, and so 0.5 raised to the 8th, 0.5 raised to 2 is just 0.5 to the 10th. This is 0.5 to the 10th. This is 0.5 to the 10th. So that's a little easier, right? So let's do our calculation. Where's my... Here we go. So I'm going to do 10 factorial divided by 10 factorial times 0 factorial times 0.5 raised to the 10th power. So that's the probability of this happening. It's 0.00097 about. So this is 0.00097. Okay. And then the next one is 10 factorial divided by 9 factorial 1 factorial, and times 0.5 to the raised to the 10th again, because it's still the same combination. And it's 0.009765, so we'll say 0.0097. What about 8? If I do 10 factorial divided by 8 factorial 2 factorial times 0.5 raised to the 10th, and it's 0.049. Okay, and we'd add all these together to get our answer. Okay, which is, should I do it? Yeah, I'll do it. In fact, that's actually easier than, I think, this plus this plus this, 0.0546. That's a lot of math, right? Good thing we have calculators. And R makes it even easier. I have a command here. P binom, probability of a binomial, and I say probability of a binomial, I want 7 from size 10, wasn't it? Size 10, a probability of 0.5, and I want lower dot tail equals false. That means, so I don't want 7. Lower dot tail means I want everything above this number. So I want everything at 7 and above up to a combination, to total of 10. And if I hit that, look, 0.0546875, 0.0546875. Okay? So you can see one of the nice things about learning a programming language is that I can take all this and just do this. That's a lot easier. On my homework for my classes, I get to do this. On my tests, I have to do it this way. So I have to know both ways. So I won't go through another one of those because I'm sure that you guys are just excited to do them for yourself. Again, if anyone wants more content for next week, shoot me a message or make a post on eCampus, and I'll give you one more week of awesome statistics content. And if you just want math to disappear, then don't. And that's okay. This is the last time I talk to you guys. It's been a pleasure. Thank you for being my students this year. I've really enjoyed my time teaching you guys. I hope you've enjoyed some of it as well. Bye.